This video will discuss the outer layers of the sun and interactions that the sun has with the Earth. So again, we have sort of a cutaway drawing here, our cores where the energy is produced. Radiation transports energy through the interior, much of the interior of the sun, until we reach a region where the temperature is changing more rapidly with distance, and convection carries the energy to the surface. And we get to the photosphere, the part of the sun that we can see. There are two more layers of the sun to discuss: chromosphere and corona. Chromosphere and corona. The chromosphere is right above the photosphere. The corona is above the chromosphere. So let's start taking a look at the features here. On the photosphere, where the visible light is coming from, there are occasionally dark areas, dark regions, bigger than the Earth for some of these. And what these regions are called sunspots. They are produced by magnetic field. If you remember, underneath the photosphere there's convection of material. Hot material is coming up to the surface. These sunspots, the material is cooler than the surrounding region, so by contrast, it looks dark. When the temperature is lower, less light is emitted. When the temperature is higher, more light is emitted. So these sunspots, even though they are tremendously hot still, are somewhat cooler than the surrounding photosphere, and they look dark. Why would the sunspot be cooler? Well, we're in a region of convection here underneath the photosphere. There's something blocking the convection, the refreshing of this sunspot material with hot material. And what is blocking it, as it turns out, is magnetic field. There are strong magnetic fields in the sun, and locally we can get a condition where the magnetic field exists in a stronger than average value in this location. That magnetic field applies force to the rising hot material and diverts it. So the hot material does not come up to the region where the sunspot is. The hot material rises and refreshes the temperature on the area around the sunspot. So the sunspots are a result of magnetic field interfering with the convection of hot material from the interior towards the photosphere. The sun has a very active surface. Granules can be seen. These granules are bright areas. They last for a short period of time. The energy radiates off, and then the granule becomes darker because it's cooler. It emits less energy, so it appears dark compared to the surrounding granules that are very hot. As the material cools off, it sinks. So all of these cells you see here, these granules, the bright ones are where more recently that material has convected up to the photosphere and is hot. The dark areas, that's where that material has been on the photosphere for a considerable time and is now sinking back down to the interior of the sun. These granules, are the size of Texas or so forth. They're considerable size. But we do have this evidence of convection. Hot material rises, gives off its energy, becomes dark, and then sinks back down. Back to the sunspots, just a size comparison here, 2012. There was a large sunspot group, the Earth here, Jupiter here. Jupiter is large, and we're getting something comparable to the size of Jupiter. 1947, some very, very large sunspots were observed on the sun. And again, these sunspots are regions where the material is a little bit cooler than the surrounding photosphere material, so they don't give off as much energy, give off as much light. They appear to be dark. They are not dark, they're not cold, but just by contrast with the surrounding areas, they look to be dark. The sunspots can be measured in terms of their magnetic field. So this image of the sun shows us what is happening in regards to magnetic field, with the white being one magnetic pole, north or south, doesn't really matter, and the black being the other magnetic pole, north or south. We see in the sunspot regions, there are stronger than average magnetic fields. There's sort of a bland magnetic field across the disk of the sun, but where there's a sunspot, we get this separation of magnetic poles and stronger than average magnetic fields. And again, the magnetic field is interfering with the convection of hot material from the core. A more close-up view of a sunspot, and as a movie, these lines move. There's a flow of material, and very interesting. That's, again, could be artwork, but it's a real place in the universe, a sunspot. Where it looks dark here, that's cooler. It's not really cold, but it's cooler than the surrounding material, so it doesn't give off as much light and looks dark. But the magnetic field is applying force to the gases that are here and causing this kind of swirling type structure. The magnetic field is creating this feature. So sunspots have been observed back into the 1600s, and individuals have counted the sunspots and plotted where they are located on the sun. So we have the equator of the sun in the middle of this chart, and we have year by year a count of how many sunspots occurred and where they occurred in terms of latitude on the sun, how far away an angle from the sun's equator. And you can see here there is a pattern, there's a trend. There's a start to the sunspot cycle, and let's pick this 1880 chart here. It's 1880 time. We have the sunspots starting further away than usual from the equator, up to around 30 degrees north and south. That's where we find the sunspots. And as the sunspot cycle continues, the spots start appearing closer to the sun's equator. Closer to the sun's equator. The graph down below tells us how much of the area of the sun was obscured by sunspots. And you can see it's not great. This is percentage. And we're not even going up to 1% of the area of the sun being sunspot area. But so back to the diagram up here, the sunspots start a cycle around 30 degrees latitude, either north or south. As the cycle continues, the spots form nearer to the solar equator. And then there's a time when there are no sunspots. Then we get the sunspots occurring again. This takes about 11 years from the start of one cycle to the start of the next cycle. However, there's another change that occurs here. This magnetic field. The magnetic field for this cycle is, in terms of where the north and south poles are, it's reversed from the magnetic field of this cycle. So say in this cycle from 1880 to 1890, the north pole of the sun was a magnetic north pole. In this next cycle, the north pole of the sun, in terms of its rotation axis, is now a south pole. And then it's a north pole, then it's a south pole, then it's a north pole, then it's a south pole. The sun's magnetic field switches back and forth in its polarity as to whether the magnetic pole is, the north magnetic pole is near the north pole of the sun, or vice versa. The south magnetic pole is near the north pole of the sun. So every 11 years, the magnetic field goes to zero and then restarts with the magnetic directions reversed. The magnetic field of the sun is most likely caused by electrical currents inside the sun. Again, conducting material that is transporting charge, and again, electricity, electric current, creating magnetic field. That's our hypothesis. It's a dynamo model, just as we have discussed for the Earth and Jupiter and so forth. So here we are with counts in the 1960s was a little higher than usual activity. Above a sunspot, we can sometimes see flares. And this is a sequence of 3 photographs. You can look at the timestamps down here. So 327, 342, 412, roughly 45 minutes from beginning the first frame to the last frame. In a flare, a great release of energy occurs. And these magnetic fields can store up energy around the sunspot. They can get twisted and tangled. And there can be kind of a release of that twisting and tangling when a flare occurs, and magnetic energy causes a heating of the solar material. So it gives off more light. And not only more light, but X-rays. So here's an X-ray photograph of the sun. And where you see the whiter, the brighter areas, that's where more X-rays are being emitted. And we see this flare occur, and it overloads the detector. These vertical spikes here, there's just so much energy coming in that the detector has been overloaded and registers X-ray light in other cells along the vertical bin here. But a view of the sun using X-rays. And I would ask you, what type of material emits X-rays? Very hot or very cold? And you should say very hot. And that is what's happening above the photosphere. The sun's atmosphere actually increases in temperature. And by the time we get out to the corona, the outer layer out here, we're into the millions of degrees of temperature. Is there significant hydrogen fusion out in the corona? It has a very high temperature. The answer is no. The density is too small. Even though the temperature is very high and the protons are moving very fast, the density is too small, and the temperature is borderline for fusion in any regard. But a key problem is that there's not enough objects out here, protons, to hit together with enough probability that they will collide. There's too much space in between the protons. Density is too low to have the corona be the source of the sun's energy. Again, taking a look, basically the photosphere is the sphere that you see here, but a prominence, material being guided by a magnetic field, again a sunspot in this top region, but a prominence where we see gas material kind of separating from the surface of the sun. Another one here, a big kind of arch of material, and these arches tend to follow magnetic field lines. When we have a solar eclipse, the disk of the moon is very nearly the size of the disk of the sun, apparent size on the sky. So a solar eclipse, the moon can cover up the sun, and we can see the chromosphere, this red glow around the edge. That's the chromosphere. Why do you think the color is red? This is a true photograph. It's not fake. The chromosphere does give this red color. What you're seeing is light from hydrogen atoms. And the most probable type of light to be emitted from a hydrogen atom in the visible spectrum is red in color. So you're seeing light from hydrogen atoms to make the chromosphere. Further out, you have the corona, kind of a glow, very high temperatures. There are loops that extend up from the photosphere into the corona. These loops, again, are created by magnetic field, creating force on these charged particles, and the charged particles follow the loop, the magnetic field. So this one's kind of face on. These others, you're looking at kind of a side view of the magnetic field. Sometimes we can get denser material above the photosphere and create a filament. So this filament is blocking the light emitted by the photosphere below the filament. So this would be one of those big arches. It's up above the photosphere disk. It's not down in the photosphere. It's sticking up above. And again, magnetic field creating the shape. Again, at the solar eclipse, when we cover up the photosphere, the corona does emit visible light. Now, the photosphere has a temperature of about 5,800 Kelvin. That's best determined by studying the absorption lines, which lines are present and how wide the lines are. This agrees with the number by studying where the peak of the solar spectrum is, what color of light is most probable to be given off. And that gives about 5,800 Kelvin as well. We also can measure the total energy coming from the sun. That's related to the temperature of a black body, and that's in agreement, about 5,800 for the temperature of the photosphere. But during a solar eclipse, we cover up the photosphere, and now we can see the corona. Again, millions of degrees temperature here. And astronomers, when they first studied the spectra of the corona, were puzzled because they saw spectral lines that did not match any element that was measured in the laboratory. After several years, it was realized that what's happening here is the corona is extremely hot, and the light that was being measured was from highly ionized atoms that don't occur in a laboratory. But with the temperature of millions of kelvins for the corona, the collisions are very violent and strip off electrons from atoms, many electrons from the atom. And that causes the atom to emit a different spectrum than a neutral atom would emit in a laboratory. So the corona gives off X-rays because it's very hot. It has a spectrum that doesn't match normal neutral atom spectra, but the spectra indicates that the atoms here are highly ionized because of that high temperature and high speed. It's likely that magnetic fields are important in carrying energy from the photosphere up into the corona and kind of stirring the corona. Another picture here of the corona during a minimum in sunspot numbers. And here we have an X-ray photograph of the photosphere. And again, up above the photosphere for some of these arches, these prominences. Again, where it's bright here, that's hotter material emitting X-rays. And then we have the case of a comet in 2011 that passed through the corona. And you can see it, tail is leaving behind there, and more ice dissipating. And this comet made it around to the other side of the sun. Coronal mass ejection, when there are huge mass of material that gains enough energy to escape from the surface of the sun. Here's the size of the Earth for comparison. And here we have hydrogen and helium, again, being influenced by magnetic fields and forming these arches. Earth down here again, and looking at the storm above sunspot region, and again, coming from one area to another. So magnetic field lines have these kind of polar nature, north and south poles. But we're seeing coronal mass ejection here, this material moving outward away from the sun. So as that material moves out, that's a space weather situation. We have protons and electrons and some ionized atoms moving towards the Earth or some other planet. The Earth's magnetic field protects us and guides that material towards the poles and away from direct hit on the atmosphere of the Earth. Just another drawing of this. The lines are the Earth's magnetic field. It gets pushed in on the side towards the sun. It gets stretched out on the side of the Earth away from the sun. And particles can kind of collect in here and then periodically drop back down into the Earth's atmosphere, creating the aurora. The magnetic field of the Earth guides these particles towards the north and south pole of the Earth and giving us the aurora. Little movie here of the sun impinging on the Earth's magnetic field and how the Earth's magnetic field responds to that material coming into the Earth. And then space weather. So this is swpc.noaa.gov, and this site is still active, but we get space weather that's being plotted for us here. And different measurements are taken. Magnetic field up in this graph, the white being the total magnetic field out in space. We have some angles of that's being recorded. Density of the solar wind, the speed of the solar wind, and the temperature of the solar wind. So there are spacecraft that are taking these measurements. This is 2012. Here's for 2013. You can see the speed decreasing. And 2014, December 2nd. Again, in this particular sequence, this is during a day, and we have the speed decreasing. So there we are, space weather. Then in terms of sunspots, again, I said that people have been counting them. Notice here, this blue rectangle is not on top of some spikes here. This is called the Maunder Minimum, when there are very few sunspots recorded for many years, from sort of the middle of 1600 into the early 1700s. There were fewer than average sunspots by a great deal, just about 0 sunspots on the sun, this Maunder Minimum. It's never repeated for this span of time, but there's something happening. The sun's magnetic field was weak at this time, so we did not get sunspots forming. And we should mention this too, there is a connection between the sun and the Earth, not just for creating aurora with solar particles coming into the sun, but there is a connection, a little bit of connection with weather on the Earth, in that this Maunder Minimum, this time of low sunspot number, was a very cold period for the Northern Hemisphere of the Earth. There was more ice skating done, more throwing of snowballs as the winters were lasting longer. The summers were not as warm. But there is an apparent connection that when there are fewer sunspots, the Earth gets colder. When there are fewer sunspots, the Earth gets colder. That's the conclusion of this Maunder Minimum. So you should write down some questions, bring some questions to class, ask your instructor.